So now we'll look at higher order partial derivatives. So remember, for a function of a single variable, I could say d squared by dx squared of f of x when I wanted to talk about the second derivative of f of x. And what I mean by this notation is take the derivative of f of x with respect to x one time. The thing in the square brackets here, that's going to be another function of x, and then I'm going to take the derivative of that again with respect to x. And then I can also use the notation, so the derivative of x with respect to x, I can call, derivative of x with respect to x, I'll call that f prime. And if I take the derivative of that again, we use the notation f double prime. So for a function of several variables, I'm going to do pretty much the same thing, except just with partial derivatives. So for instance, if I wanted to take the derivative with respect to x, or the second derivative with respect to x, second partial derivative with respect to x of a function e to the xy, so maybe we can highlight that part at least. What I mean is take the derivative, take the partial with respect to x of e to the xy. That's going to give me another function of x and y. And then take the partial derivative of that function with respect to x again. And so if I just go ahead and evaluate that, I'm going to end up with y times e to the xy by taking the derivative of this with respect to x once. And then another y will pop out when I take the second derivative. So I end up with y squared e to the xy. So there's a bad example of how not to do the chain rule by just doing it all explicitly. And then similarly, if I want to take the second partial derivative of e to the xy with respect to y, I'm going to do exactly the same thing, except I'm just going to have partial y's in the denominator. And in this case, this is such a simple function, I could just relabel the x and y. So we can kind of skip the computation and just see that the output is going to be, in this case, x squared times e to the xy. But for functions of several variables, there's now also the possibility of something called a mixed partial derivative. So I'm going to keep the same idea as I had in the middle section of the slide, where I take the derivative with respect, say the partial derivative of my function with respect to one of the variables, and then repeat. Except when I repeat, I can take the partial derivative with respect to a different one of the variables. So in this case, I'm going to take the partial derivative first with respect to y, and then with respect to x. So you can kind of think of this thing here as an operator. And so it's going to do something to this function. And the part that's closest to the function, that's going to happen first. So if I were to write this out using slightly longer form, when I say partial squared, partial x, partial y, I mean first take the partial derivative with respect to y of my function. That's going to give me another function of x and y. And I'm going to take the partial derivative with respect to x of that function. So here I've just evaluated the first partial with respect to y. So we got the same thing we got up here. But now this time it's going to be slightly more complicated, because I'm going to take the derivative of this now with respect to x. So now this is a product of two functions of x. So it's x is the first function, and then e to the xy is my second function. So I have to use the product rule. And so again, just to make this all fit on one slide, I've skipped probably some essential work, but I hope it's correct. So I have the derivative of the first function times the second function. So the derivative of x is going to just be 1. So the first term in the product rule is going to be e to the xy. Then plus the first function times the derivative of the second. So I'm going to take x times the partial with respect to x of e to the xy. And we already worked that out above too. So I have e to the xy plus xy e to the xy. Oops, what have I done here? Okay, my arrow is not working anymore. There it goes. And so now this is going to probably bring up the question, what is the relationship between, so here I'm doing the mixed partial, taking the partial derivative with respect to y, and then the partial derivative with respect to x. And here it's just the other way around, first with respect to x, and then with respect to y. So we already saw that if I did it y first, then x, this is the function that I got. And now let's look at what happens when I do it with respect to x first, and then with respect to y. So first I'm going to take the partial derivative with respect to x of e to the xy. And that's just going to give me y times e to the xy. And now again I have to use the product rule to take the derivative of this. So it's the derivative of the first function. So the derivative of y with respect to y is just 1 times the second function. So that's where this e to the xy comes from. Plus the first function, so that's my y here, times the derivative of the second function. And we've already worked this out. This was just x times e to the xy. So I end up with e to the xy plus xy e to the xy, which is what we got for the first one. And so when I have this sort of very symmetric with respect to differentiation function, I find that the mixed partials are equal. So it doesn't matter if I do dx dy or dy dx. I get the same result. So, but this function that I chose, it was easy to work with in terms of taking its derivatives. But because of this symmetry, maybe we should try it with a little bit more complicated function to see what happens. So I think I chose this function from the textbook. It was not fun to take the derivatives of this. So to get the second partial with respect to y and then respect to x, first I'll start out by taking the derivative of this with respect to y. So let's see. So the first thing I'm going to do is make my u substitution, just to avoid making mistakes with the chain rule. Usually what gets me is the minus sign up here, because that's, if there's a minus sign here and a minus sign here, for some reason I tend to have about a 50% chance of missing one of those, or getting it wrong, I suppose. So I also did the partial derivative with respect to y of the first term here, just because it was easy. So by the power rule, the y is just y to the 0. So I have x squared plus the partial derivative with respect to y of e to the u. So that begs for the chain rule. And so that's just going to be the derivative of e to the u with respect to u, which luckily is easy, e to the u, times the partial derivative of u with respect to y, which I'm going to get just exactly like the first example by taking the derivative of my substitution. So let's see what I end up with here. So I have x squared minus 3xy squared e to the minus xy cubed. And in fact, since we've already taken the derivative of this a few slides ago, I didn't have to do this bit. I could have just used the derivative I'd already computed. And so now I want to take the derivative of this guy, the partial derivative, with respect to x. So again, I'll do the first term, just because the derivative of x squared is easy. By the power rule, I just get 2x. And then this minus is going to appear here. And then I'll take the derivative of this term by treating it as two functions, 3xy squared and e to the minus xy cubed. And so I'm taking the derivative now with respect to x. So the derivative of the first term, that's easy. That's just got x to the 1, so the x is going to go away. So I end up with 3y squared times the second function, then plus the first function, so there's my 3xy squared, times the derivative of the second function. And so just plugging all of this in and distributing this minus sign gives me this. And now all I have to do is plug in what u is and what the partial derivative of u with respect to x is, which I got just, again, by taking the derivative of this with respect to x this time. And so I end up with this somewhat unhappy looking formula here. But at least it's something that doesn't look like it's going to have a lot of symmetry. Like if I change the x and y, they shouldn't be the same. And so now we'll repeat the same calculation, but here I'm going to use x first. So this time, the last time I did y first. And now this time I'll do x first. So again, the first term is going to be pretty easy to do, so we'll just do that. Second term, I'm going to make my u substitution so I can see myself using the chain rule. So I'll let u equal minus xy cubed again. So the first part, I'm treating y as a constant and then taking the derivative of x squared. So power rule just says that's going to be 2x and then times y. And then I need to take the derivative with respect to x of e to the u. So by the chain rule, that's going to be e to the u times the partial derivative of u with respect to x, which again I get just by taking the derivative of my substitution. And now I need to take the partial derivative of this with respect to y. So again, the first term is going to be easy. That's just y to the 1, so that's going to be 2x. And the second term, I'm going to need to use the product rule. So the functions will be y cubed and e to the u. So the product rule says it's the derivative of the first function. So this is the derivative of y cubed by the power rule, times the second function, plus the first function times the derivative of the second function. And so we've done this several times already, so just skip this line and just plug in the results. Oops, 2 times. And so we get another sort of unhappy looking formula. But I think on the next slide, I put them together, and those were actually the same formulas both ways. So that sort of gives us some hope that probably these things are equal regardless of what order you take the derivative. And if you take a more serious math class, you can actually prove this. I'm just going to give the statement of the theorem. So if all of the partial derivatives of order k, so order k means how many times I've taken a derivative. So if I take the second partial derivative, that's a derivative of order 2. Of the function f of x exist and are continuous, then the order in which the partial derivatives of f of x of order at most k, so as long as I don't try to go beyond k, then the order that I do those derivatives doesn't matter. I'm going to get the same mixed partial. And so just like I made an array to hold the first derivatives, I need to make an array now to hold the second derivatives. And this array is going to be called the Hessian of f of x. And we can use the notation d squared. So that 2 just means essentially take the derivative twice. But in this case, because we're talking about functions, so the first one has n inputs. Then I end up with the gradient, which has n outputs. So that's a function that has n. When I evaluate the gradient at one point, I get n results. And then I'm going to take the derivative of that again. So I'm going to get an n by n array of mixed partial derivatives. And so down the diagonal of the array, so the diagonal, for some reason, when people say that, they mean top left to bottom right. This going up, bottom left to top right, it's also a diagonal, but nobody means that when they say diagonal. So the diagonal elements are just going to be taking the derivative, the partial derivative of the function with respect to the same variable twice. So in that case, I can kind of compact this notation. This means partial x1, but it's the same thing, so I just write it as squared. And then in the off-diagonal elements, the first row, I take the derivative with respect to x1, the partial derivative with respect to x1 first. So the x1 is going on the right side here. And then I take the partial derivative with respect to x, whatever column I'm in. So if I'm in the second column, I take the partial derivative with respect to x2. If it's the nth column, I take the partial derivative with respect to xn. And remember, because of the theorem that I had on the last slide, this function here and this function here, so this is x1, x2, and this is x2, x1. So if this function is well behaved, then these two terms will be equal. So there's kind of a nice symmetry here, which means that even if you forget precisely by the definition which order these are supposed to go in, you're probably going to get the right answer anyways.